Hello students, in today class we will study about electric dipole examples, electric dipole definition and electric dipole placed in a uniform electric field. So first of all, what is electric dipole? Electric dipole is a system of two equal and opposite charges placed at a very small distance. Let us see in this diagram. These are two charges of equal amount but of opposite signs, and the distance between them is very small, that is 2l. Then this system is known as electric dipole. And another quantity defined in this relation is vector p, that is known as electric dipole moment vector. Examples of electric dipole molecules are HCl, H2O, HBr, Ki, CH4, CO2, NH3. These all are examples of electric dipole molecules. This arrow is showing the direction of vector p, that is electric dipole moment vector, and its direction is always from negative charge towards positive charge. Its magnitude is given by p is equals to mode of vector p is equals to q into 2l, that is magnitude of the charge multiplied by distance between the charges. From here we can find out its unit. Unit will be, the unit of charge is coulomb and unit of length L is meter. So the unit of electric dipole moment will be coulomb into meter. Now we will see what happens if we place our electric dipole in a uniform electric field. Suppose this is a uniform electric field. Uniform electric field means these lines of force are equally spaced. This interval and this interval are equal, and they are equally spaced lines. Then this electric field is known as uniform electric field. If these lines of forces are not uniformly spaced, that is the interval between this line and this line are not equal or constant, that is they are not equally spaced, then this field is known as non-uniform electric field. So in our case this is uniform electric field. This is our electric dipole. This is our negative charge q, this is our positive charge q. The distance between them is 2l. Okay, and this electric dipole is placed at an angle theta with this electric field E, that is this angle is theta. The axis of electric dipole making angle theta with electric field E. If we increase, and another concept is, upon this positive charge q there will be a force in the direction of electric field, and upon this negative charge there will be a force F in opposite direction to the electric field. This means that on positive charge there will be a force in the direction of electric field, and on negative charge there will be a force in the opposite direction of electric field. If we increase this line of action of force and draw a perpendicular from positive charge q, we will find a triangle A, B, C. In this triangle this angle will be the theta, because our electric dipole is placed at an angle theta with electric field E. Applying sin theta in this triangle ABC, in triangle ABC sin theta is equals to AC upon AB is equals to AC upon AB. The value of AB is 2L implies AC is equals to 2L sine theta. So we have seen that if we put our electric dipole in a uniform electric field, on this end there will be a force in the direction of electric field, and on the another end there will be a force in the opposite direction of electric field, like this. They are equal and opposite forces. And hence we can say that they are making a couple of force, and this a couple of force equal and opposite forces will try to align our electric dipole in the direction of electric field, like this. So we can say that on electric dipole in a uniform electric field there will be work a torque, and the tendency of this torque will be to align the axis of electric dipole in the direction of the uniform electric field E. So our next heading will be electric dipole in uniform electric field. So torque on electric dipole in uniform electric field will be equals to force into perpendicular distance between forces. This is the formula for torque. Force to perpendicular distance between forces. Force is F, and perpendicular distance between forces is, this is the first line of action. If we increase in backward direction, this, and this is the second line of action, and the perpendicular distance between them is AC. So we can say that the perpendicular distance between forces is AC, this, and AC is 2L sine theta. The value of F is Q into E into 2L sine theta. From where this QE? Because we have E is equals to F upon Q, implies F is equals to E into Q. From here we have put the value of F at this place. This will be QE, and it is written as Q into 2L into E sine theta. This Q into 2L is P, and it will be P into E into sine theta. Hence the value of torque working on electric dipole will be tau is equals to P into E into sine theta. This torque tau, and in this formula P is electric dipole moment, E is intensity of electric field, theta is the angle between the axis of electric dipole and electric field. Now special crisis arises, special cases. Special case first. If theta is equals to 90 degree, this means this is electric field and this is dipole, and this dipole is placed at an angle 90 degree with this electric field, then theta is equals to 90 degree. This is electric field, this is electric dipole, and the angle between the axis of electric dipole and electric field is 90 degree. So torque on this electric dipole, P into E into sine 90 is equals to P into E. Sine 90 is the maximum value of sine, and it is 1. So tau will be maximum. Tau maximum is equals to PE. Second special case, if theta is equals to 0 degree, this means This is our electric field and this is our electric dipole. It is negative charge, it is positive charge. This electric dipole is placed parallel to electric field E and the angle between them is 0. Then torque on this dipole P into E into sine 0 and it will be 0 because sine 0 is 0. In third case, if theta is equals to 180 degree, then torque tau is equals to P into E into sine 180. This means if our electric dipole is placed in opposite direction to electric field, that is this charge will be plus q and this charge will be minus q, and the direction of E electric field will remain same, then this will be 0. So in this case torque on electric dipole remains 0 because in our this lecture we have seen about electric dipole moment, its example, its definition, and what will happen if we place our electric dipole in a uniform electric field. In our next upcoming lectures we will see what will happen if we rotate our electric dipole in an electric field, and the electric potential energy of electric dipole and electric field produced by electric dipole, electric potential produced by electric dipole. So must remain in touch with our videos, and in next lectures we will continue this series. Okay then, and thank you.